Okay, so here we're just going to calculate and prove how we can calculate the BM. Okay, imagine that we're just looking at the pontoon in the side view. In the side view, if it's tilted a little bit, we're just gonna try to just calculate the restoring moment of RM, restoring moment of RM about like the point C, for example. That is like they're going to calculate it here. So imagine we're just gonna have like an infinity layer, yeah, this hatched layer, infinity layer from like this is the plan, the B is the plan of the pontoon, and the A is the side view or the cross section of the pontoon. And this hatched area, like the shaded area, like the area that has been under the water, this is the above the water because of the tilting, and we have like a shaded, or sorry, the hatched area or the infinity layer, and we're just going to calculate this one. Because of like this tilting, the angle created here, we can call it like the delta theta, and the distance from that is like the x, and this delta theta is also the same as this one as well. Okay, and the area here is the delta A. Delta A, we just bear in mind, we just need to just calculate it all together. Okay, let's just start. So we're just gonna write in this triangle ADC or ADC, we can just write delta theta or tangent delta theta is equal to h. H is the height of this over x is the opposite to the adjacent. Okay, or if we arrange this formula, we can just write h is equal to x tangent delta theta. Once the angle or the like delta theta is very small, that is like the case for us, you can assume that the tangent delta theta is equal to delta theta in radians. Okay, so substituting the tangent delta theta by delta theta here, we can easily write h is equal to x delta theta. Okay, so in the next thing, so if we just look at the element shaded has got like a delta A. This kind of like the hatched area has got a delta A in plan view. Okay, the area of the delta A, and we know the height is going to be calculated here. H is x delta theta in the vertical section or the side view. So the volume of this kind of like a shaded or hatched area is equal to H that we calculated here times delta A from the plan, okay, H times delta A. It's a very simple formula for the volume. And if you're just going to substitute H from x delta theta, and delta A is written here, we're just going to have like the volume is equal to x delta theta delta A, okay? And the weight of that section, hatched area, is equal to rho GV. Okay, so you need to just times rho G to the like the volume that we just wrote it here, rho GX delta theta delta A. And the moment of this elementary buoyancy force about point C, okay, is equal to all this term times X. Okay, the weight times X. This is the buoyancy force or the moment of this buoyancy force. So rho GX squared delta theta delta A. And if you're just gonna say the moment about this point, we're just gonna have like the RM, which is like the oldest term integral from this point, like for example, from the 0 to the A to the whole area. So that one is like you can just take out rho G delta theta out of the integral, okay, because there's no like the elements of variables inside the integral, and that's fine. Rho G delta theta outside the integral start from like a point from here, from the 0 to point A, or like the whole area, let's say, for example, from here to here, from the beginning A to the whole area to just calculate for the whole like the restoring point. So this integral, but the x is variable definitely for each like this section. X is variable times delta A as well. Delta is another variables as well. and that's like the area, integral of the area, like the two-dimensional integral. But we know that the second moment of the area about the x axis is equal to integral x squared dA. So if we're just going to substitute here, we're just going to have like the restoring moment, or Rm, that we wrote it as like the acronym, is equal to rho g delta theta is. Okay, so this is like a part of this kind of like the proving the formula. So Rm is equal to rho g delta theta I, or the second moment of the area that we just prove it here. On the other hand, if you look at this example, the total restoring point or moment about point B, okay, if you look at this kind of like the example, can be written different way, can be written based on the total buoyancy force. So the total buoyancy force restoring point can be written as like the F times the lever R, okay, the force lever, the buoyancy force lever on BB star. You can just easily, by the other way, you can just calculate the restoring point. And F is the buoyancy force, is a rho GV, and the V is the volume of the water displaced, multiplied by the lever arm BB star. So you're just going to write this one Rm different way. Rm is equal to F times BB star, and we know the F is rho GV. If you're just going to put it here, Rm is like the rho GV BB star. Okay, BB star is like the length of the here. However, from the geometry, you know, this in this triangle BB star M, we know that like the delta theta, okay, delta theta is like the angle of the tilt, is equal to the opposite BB star divided by the hypotenuse BM. Okay, if you rearrange this one, BB star is equal to BM, hypotenuse times sine delta theta. The same rule, once the angle is very small, which is the case here, the sine delta theta is the same as the delta theta in radians. So we're just going to substitute here delta theta rather than sine delta theta. So BB star is like a BM delta theta. If you're just going to substitute BB star from in the top formula, we're just going to have like the Rm is equal to rho GV BB, rho G V BM delta theta. That's something that the BB star has been replacing here from this formula. And if you're just going to compare the formula in the previous slide and the formula in here, left-hand side, we're just going to calculate the restoring moment in two different ways. So the right-hand side is expected to be the same. So if you're just going to equal the right-hand side, you can cancel the rho G from the left and right-hand side, and the result, and the delta theta as well. And the result is equal to the BM. The BM is equal to the I, the second moment of the area, in the longitudinal, like the XX axis, divided by the volume. So that's like a proof of that formula. And remember, just a reminder that the second moment of the area, this is a formula for that, is an integral of the x squared ds. It's just going to be like, for example, from minus d second to the d second. And that's like the proof of that one, if you remember the way that we're just going to calculate that one, LD cubed over 12, that we know this one from the past